Okay, good morning. Our first talk of the day, of the last day, is by Gaetano Lambiase, who's going to tell us about QFT approach to gravitational wave physics. Go ahead.
Thank you very much for invitation. The talk today regards the approach of quantum field theory to gravitational physics. And in particular, I will focus on the ghost theory and the theory without ghost. This way? Is it better? This research line is in collaboration with Shinji Mukoyama, Tame Poddar, and Anna Chiara Rescigno. So the plan of the talk is I will present to you the so-called four-order theories of gravity, ghost-full and ghost-free case, which means that essentially we implement generativity with quadratic variant curvature terms that present the ghost, is a theory with the ghost, and we implement this theory, actually it's a stellar theory, with the additional degrees of freedom that take into account the torsion. So we pass from Riemann to Riemann-Kantian geometry. Then the target is to calculate the gravitational wave emission by binary system in the ghost field theory. And for this, I will present you in some slides how effective field theory works for generativity. Then what we learn in this chapter, we apply directly to ghost field theory. And then I will discuss with you some preliminary results about bands on coupling and mass from physical data. Okay, so from generativity, we know that in the infrared regime, apart dark matter, dark energy, the generativity works very well because it passed the higher precision test. Think about gravity propagation of black holes and so on. And in particular, the prediction and observation of gravitational waves make generativity as the best theory of gravity that we have at the moment. However, in the ultraviolet domain regime, we have some problem. At classical level, we know that there are some singularities related to cosmological singularity at t, the cosmic time t equal to 0, and the black hole singularity at r equal to 0. At quantum level, we know that generativity is not renormalizable. And let me tell you also that generativity actually has been tested till distance 10 to minus meters, so it will be good to go below this distance. Now, it's clear that generativity by itself is not enough to solve all the problems that we have described here, so we need some kind of generalization. And we know that there are a plethora of models that generalize Einstein theory, but as I told you, I will concentrate in particular in higher order curvature terms, and in particular in four-order gravity. So it means that in our Lagrangian, we will take into account only this quadratic term. The generalization will include the torsion term. As we will see in one moment, these quadratic terms solve some problem regarding the renormalizability, but present a big problem related with the cost. In fact, let me give you a shot of this problem. If we work in the framework of generativity, this is the action, of course, we have a second derivative of the fluctuation of the metric, and the propagator goes as 1 of p squared. Then when we go to Feynman diagram, we end up with the calculation of this kind of integrals, and here appears the so-called superficial degree of divergences. So this parameter d is related to the loop inside the diagram, internal line, vertices, there is this topological relation. But what happens is that in generativity, this parameter d is related to the loop. So it grows with the loop order. Going up with the loops, the divergence becomes more severe. We need the control terms that increase the order of the derivative. The final result observed by Stell was, okay, generativity is not renormalizable. Instead, if one considers, as Stell has done in his seminar paper, quadratic correction to the Einstein theory, what happens is that redoing the calculation of the superficial degree of divergence D, in the stellar theory, D is a constant, is equal to 4. So it's independent of the number of loops that you met in the calculation. So D is independent L. Reading from the stellar paper, no matter how many loops one adds, divergence never require operators with more than 4 derivatives. So it means that all the quadratic terms inside the stellar theory are enough to cure divergences. So the theory is a power counting renormalizable. This beautiful result, unfortunately, presents a very big problem related with the ghost, because when we stay in a general relativity framework, the propagator is simply related to k squared with some project operator that we will see later. The form is not important here. But in the stellar operator, due to the fact that we have this quadratic term, then two additional modes turn on with the mass M2, M0, which are related with this constant alpha and beta here. The problem arises because for the mode 2, we have this minus here. The minus here means that if you compute the normal state of a particle, the normal state is negative. On top of that, also the unitarity is violated. So the conclusion of Stell was this theory is perturbatively renormalizable, but due to the presence of ghosts, the unitarity is lost. When we have a ghost in a theory, at some point we have to decide what to do if we want to work in this framework. It's clear that if we work in the regime where ghosts are important, are dominant, of course the validity of the effective theory requires some caution, and in particular what happens, the loss of the theoretical control. So what people do usually is to set the mass of the ghost to infinity. So it means, okay, let's remove this dangerous term here. As effective theory, we are saying that this ghost mass works at large energy. We stay far from this large energy. So as effective theory, we can, in principle, remove these terms and work with the gravity terms and these additional M0 terms here. Other approach consider the possibility to give some interpretation of this spin to ghost, and with some prescription related to Feynman propagators and so on. But on top of that, the conclusion is that if ghosts are there, they continue to be there, and the situation didn't change till now. So what I will present in this talk is a possibility to generalize the stellar theory in order to remove the ghost, and in this theory, try to see what happens from an observational point of view. So the model which I'm referring is the model by Aoki Mukoyama, proposed some years ago, in which you see the Einstein-Hilbert-Lagrangian plus quadratic terms are implemented with the terms dependent by curvature. These terms actually has this kind of form, but they are constructed starting from the connection, written in terms of Levi-Civita connection, so gravitational sector plus torsion. With this tensor, you can construct this kind of torsion, tensor actually. And with these tensors, you can construct all possible combination between tensor, rich scalar, and so on. So the basic fact of the Aoki-Mukoyama model that they have 16 dimensionless parameters, and that in a very clever way, they use it to remove all the instability, all the ghost. The second point, they include, apart from the Planck mass that is related to gravity, a new mass, the torsion mass MT. So in this framework, when you quantize the theory and it goes to propagator, you find that the propagator assumes this form. It is constructed in such a way. You can have still two massive modes, M2 plus and M0 plus, where M2 plus and M0 plus are related, of course, to this coefficient entering in the theory. But the basic point, here we have a plus. So the ghosts are removed. And the theory is constructed in such a way. When M2 plus M0 plus goes to 0, you recover immediately Einstein theory. Instead, to recover for all the theories of gravity with ghost, stellar theory essentially, you have to consider the limit mt goes to infinity, which means that the mass M2 plus coalesces to M2 in the stellar theory, the mass M0 plus coalesces to M0, and we recover the propagator with the minus, this dangerous minus here, okay? So, before to compute the gravitational, sorry? Yeah. Sorry? In where? In the full theory of stellar, you mean? Yeah, actually it is not there. Ghosts are not here. No, actually, calculation, you have to make a variation also for the torsion, not only for the metric. So we have two kinds of variation. One for the metric and one for the... No, it's not, you have a fluctuation of the torsion. Yes. Propagator, sorry. Yeah. Yeah, but sorry, maybe I don't have the slide with me, but the theory is constructed in such a way when you make the perturbation, you have to make a perturbation for, you write everything in terms of field bind. Field bind, you have background plus perturbation, and this goes for the matrix. Field bind for the spin connection that give you the contribution that are here. So there are these two kinds of perturbation that they do in their paper. Okay. So we are here. So before to calculate the emission of gravitational waves from binary system in the Aoki CNG model, let me present what is the strategy that usually people do. Actually, important contribution given by Accioli. So here we follow Accioli and collaborators paper. The important relation we need is the connected Feynman diagrams WV, which is related to the generator zeta T here. And the second point is the energy, Bidding energy that is defined as the ratio between the connected Feynman diagrams with the time interval this time interval that we cancel out from final calculation. WVD is written this form. The calculation is done for the dimension. Here we have the energy momentum tensor, T mu nu, T alpha beta related to the gravitational source, and D is the propagator. So, skipping some details, using the energy momentum tensor for two masses, M1 and M2 located at A1, A2, one can compute the connected Feynman diagrams in this way, divided by T divided by M, we have the potential between the two masses, and P0, 0, 0 is the numerator essentially of the propagator. The calculation is done, in this case, in the static limit, and then you recover in 4 dimensions the usual Newtonian law. Okay, they have done also for the dimension. So what happens instead in the gravitational wave emission with effective field theory approach? Let me just recall that when we say in general relativity, h mu nu satisfied from Einstein equation, box h mu nu equal to 0, we expand h mu nu in terms of Fourier modes, And here we have the polarization tensor that satisfies these properties. In particular, they satisfy this relation, which is important for us because this relation enters in the definition of the emission rate of massless graviton, because here is defined this way. We have the square of the energy momentum tensor coupled with the polarization tensor, delta mu that preserve the energy. Then when we squared this term, appears here the product of the polarization tensor. Using the properties of the polarization, we end up with the emission rate of massless graviton written in this form in terms of the component of the energy momentum tensor. Actually, what we need is the rate of the energy loss, which is defined in this way. And using the previous relation, this is our master equation for this kind of calculation. Using some properties related to energy momentum tensor, we can write the integration here in terms of the angular part in this form. So only this component enter into the game. So specifying the problem for compact binary system, so the energy momentum tensor is written this way. For simplicity, one consider planar motion. At some point, we introduce this fundamental frequency, and what is important is the orbit are parameterized in this form, where A is the semi-major axis and D is the eccentricity. So in our calculation, we'll keep the eccentricity in all the steps. I will comment at the end why this is quite important due to complication of the calculation, of course. Now, let me just tell you that in the final formulas, we find the Bessel function derivatives because we consider the Fourier transform of the velocity along x and y, which depends on this Bessel function. So these terms enter in all the final equation. And when we compute the energy momentum tensor can be written in this form, the non-vanishing components are assumed this form that, as you can see, depends on the Bessel function. Now, the point is, once we have all the components, we can compute all the terms inside the integral, which assume this form, and due to the presence of centricity, you see, we have this complicated expression for the first term. By the way, apart from this, when we compute the energy loss due to graviton in the binary system, we end up with this sum, and summing of all modes, we recover the Einstein quadrupole gravitational radiation. So this method works very well, at least for general relativity. Now, what happens in the case in which we have a Gauss-free quadratic gravity, the Sinji-Aiki model? First of all, let's compute the gravitational potential in this model. And as you remember, the basic point was here, T mu nu coupled with the propagator. Now, our propagator, as we have seen, is much more complicated because we have all these terms. By the way, one can do this kind of calculation, and T mu nu propagator T alpha beta can be written in three terms. A refers to general contribution, B refers to M2 plus modes, and C, written in this form, refer to M0 plus modes. Now, for a binary system, we can choose T mu nu in this form, and then we can compute the potential between two mass, which are written here. This is a Newton potential, and here the contribution comes from two modes, and we recognize here the Yukawa-like terms that enter in this kind of potential. So the total potential is the sum of these three potential, and is written here. Now, as a check of this calculation, let's see what happens when we consider the limit mt goes to infinity, and we recover the Accioli result, of course. With this interesting comment, as Accioli pointed out, that when we consider the limit L goes to 0 in the stellar theory, L goes to 0, the potential is regular, so the singularity disappears. So this is a point in favor of for all the theories of gravity. So what happens now for the radiation massless and massive mode in the Aoki-Bukoyama model? So remember that we have 3 modes, so we have to compute the contribution of the modes A related to generativity, B M2 plus, and C M0 plus. And the final contribution is the sum of the single contribution that we will write in the final formula in this way. Calculation can be done. Here are the expressions that we derived, but after very long calculation, the final result for each contribution is here. The first one is the generativity results. The second one is related to massive M2 plus graviton and assume this complicated form. And the last result is associated to massive M0 plus scalar modes. And we have this expression. I cannot here, okay, here is written. So the final expression, to the fact that we are considering this eccentricity, is a very complicated formula, of course. And there are some comments that is important to do here. We recover what is well known in literature, that due to presence of this square root, the modes M2 plus and M0 plus are kinematically allowed only if we have that M2 plus, M0 plus is less than omega. When n is equal to 1, it depends by other n is a similar relation. But it's important that in order that kinematically this mode can be activated, we must stay in this range. Second point, as soon as M0 plus M2 plus goes to 0, all this contribution goes to 0, and we recover generativity. So what happens in the case of Gauss full for all the gravity, which means to consider MT that goes to infinity, in such way M2 plus collapse to M2, M0 plus collapse M0. Well, this is an analytical result because we have expanded this square root, but the point is that the general relativity contribution cancel out because the presence of this minus here coming from the Gauss is such that the general relativity contribution cancel out, and we have an energy emission that is proportional to the omega to the 4 instead of to omega to the 6 as in general relativity. And of course, the result is strongly suppressed by M2 and M0. We can compute the orbital period decay P dot in the Hasse-Taylor effect and the radiation of massless and massive mode in the Shinji-Aoki model, which means to compute the variation in times of omega. Okay, this is a standard calculation. Because we have the potential, we can compute the force. The distance is described by A. If alpha and beta are these parameters related to these new modes M2 plus and 0 plus, one can compute the orbital frequency, the total energy, and after some manipulation, we can compute the P dot orbital period decay in a Gauss-free quadratic gravity, which assumes this quite complicated formula. And here we have the contribution coming from the emission of the gravitational waves. Instead, this contribution comes from the Yukawa-like terms that enter in this kind of theories. In the in the limit in which we pass from ghost-free quadratic gravity to ghost-full quadratic gravity, what happens? M0 collapse to M0 plus collapse to M0. This coefficient assume some other values, but what I want to point out to the attention is that the contribution in the T ABC collapse in A, B prime, C prime. So when we have a prime and C prime, it means that we are in ghost full theory. Okay. So this is the first calculation related to the orbital period decay. Now let's go to compute the evolution chip mass for this signal, gravitational wave 170817, computing the omega dot variation. Here, fortunately, some simplification can be done because in this coalitions binary system, at some point the orbit is circular. So it means that we can set the eccentricity for this system equal to 0. This is a big advantage because we can have simplified formulas. The only attention that you have to put here is that the semi-axis, major semi-axis A, now can vary with the time, and we have to substitute in our formulas R dependent on T. We refer, as I told you, to this signal GV1708 SIMVIN detected by LIGO, and due to sensitivity, LIGO sensitivity, we are interested in the orbital separation between 2,700 kilometers that written in terms of the mass in electron volt, they correspond to mass ranging from 10 to the minus 11 to 10 to the minus 13, 11. Actually, we, because I have some, not total result, but some preliminary result, I will refer in particular on this value. So in this setup, we can set the eccentricity equal to 0, R is time dependent. This is the total energy of our system, coalescence binary system. The contribution of each mode, A, B, C, when the eccentricity is 0, reduced to this readable form, at least it's readable. When we compare the total energy of the system lost in favor of gravitational waves, we can recover how the distance varies with the time, which is this quite complicated expression. Because we know the form of omega, making some derivative, we can compute how omega, the orbital frequencies, vary with the time, and we get this expression. Okay. In the limit M2 plus M2 0 goes to 0, we immediately recover the generativity result. So look, in this generalized Lagrange, generalized model by Aoki, Aiko, and Mukoyama, we have the same dependence on omega 11 upon 3 as in generativity. Now, what happens when we compute the limit for going back to ghost-full theory of gravity? So it means take the limit mt goes to infinity. Well, calculation give us that omega dot, in this case, dependent on omega as 5 divided 3. So not only we have the problem that the quadrupole formula is not recovered in these quadratic theories of gravity, but also the omega dot is dependent on omega 5 or 3, which is not consistent with the generativity. Now, some preliminary result and observation on the coefficient, but I will present you some preliminary result because actually the total analysis required to take all the parameters independent. Instead, to simplify at the moment the result, we assume that the same mass, the same alpha, just to have an idea what is happening. So we are, the complete analysis of the parameter space is understood in this moment. By the way, just to have some insight from this analysis. So, sorry. Let's compare the period decay rate with the asset error binary system. And we have done also for PASRJ, the second binary system. This is the expression for the ghostful theory, so stellar theory. And here is the result that we have. The blue line is the generativity value. The red line refers to this P dot relation. And the plot gives us this information. Oh, of course, here there is the error as reported here in this zoom. In the forward gravity with the ghost, what we have is, due to the fact that we have seen that P dot scales in completely different way with respect to generativity, we have that the standard forward gravity move in this red line. Arrived here, what happens is here is m of the order omega. So the modes cannot be activated. So we have to, the channel B1 and C1 goes to 0. And here we have only generativity. But at this point, now the important role is played by the Yukawa-like terms. So we have this kick still here. Again, we stay outside the range of error of generativity, except for m of the order of 10 to minus 18 electron volt. And then, as expected, for large mass, the Yukawa-like terms go to 0, and okay, we recover generativity. So it's interesting. Analysis, let me tell, here we are assuming that m is equal to m2, m0, but of course the complete analysis requires that m2, m0 should be different. So we have that in this range, we can recover in the forward theory of gravity the agreement with the observation, but it's clear that it's due to Yukawa-like correction, because the contribution coming from the modes M2, M2 and M0 are completely outside the range of the observation. Then we have studied also in this framework what happens if we decouple the ghost from the theory, in the sense that M2 goes to infinity. And as you can see, so we have only M0 modes. As you can see, the situation does not improve too much. In my opinion, it's worse, because for the range of parameter for M, we are completely outside the observation, and only when Yukawa-like terms goes to 0, we recover some merging with generativity and observation. Instead, in the Aoki-Mukoyama model, we can get some new bounds, because in this theory, there are no bounds actually, because it's a new theory, and we are investigating starting from last year actually. So this is the expression, the general expression for the ghost-free theory. What this plot represents is P dot with the error, and here we have the parameter alpha m such that fall down in the range of the observation. So these are the line, and so we can, for instance, put alpha 1 equal to 0, alpha 2 different to 0, alpha 2 equal to 0, alpha 1 different to 0, alpha 1, alpha 2. So we have this kind of line consistent with the observation. And here, for instance, we can set some bound for alpha 1 equal to alpha 2. When m is of the order 10 to the minus 16, we have some lower bound on alpha, which is of the order 10 to 84, something like that. Okay? Instead, maybe much more interesting information coming from comparison with the chip mass evolution for this signal, where omega dot present here the generative results and the contribution Yukawa like term and radiation associated to massive modes are written in this form. And what happens here, following, of course, the literature and referring, so following the literature in the sense that we plot not omega, but the frequency at the power 8 minus 3, and fixing the mass to 10 to minus 11, what happens here is much more clear that the ghostful theory could have some problem, because the black line refers to generativity, the red line refers to ghostful theory with the ghost, and so you see we have this line which is completely decoupled from the observation, and also in the limit in which the ghosts are absent, so M2 goes to infinity, the blue line, so they are decoupled from the theory, the blue line goes in this way, which is far from observation related to generativity. Instead, for ghost-free theory, situation is completely different because GR is this value, the green line, the gray line are the error, and we find some values for the free parameters alpha1 and alpha2 that fall down in this range. So we have something fixed M equals to 10 to the minus 11 electron volt. We have that alpha is around 10 to 75, means that we improved at least 7, 8 order of magnitude with respect to Taylor effect. So in conclusion, it's clear that generativity requires some correction. Which is the correct one? We don't know yet. Because I show you there are a plethora of models with the pros and cons, and everybody is free to choose what is the theories that he prefers. But by the way, in the framework of quantum field theory that at the moment we are interested, we have considered extension generativity with the Eiger-covered terms. And starting from stellar theory, we have seen that this theory presents 3 modes: massless spin 2 graviton, massive spin 2 modes, the ghosts that give rise to the ghost, and massive spin 0 modes. This theory is power counting remarkable, but the unitarity is lost. Extension of this model is to touch the geometrical sector, including the torsion, so moving from Riemann to Riemann-Cartan geometry. And the new additional degree of freedom consists in graviton again, massive spin 2 graviton, massive spin 2 modes, massive spin 0 modes, without ghosts. So the theory is power counting remarkable and preserve unitarity. As we have seen, the basic relation related to gravitational wave astrophysics, so the rate of emission, energy emission rate for binary system, when calculated in the 2 models, present consistent deviation, because in the cost-free theory, we have that the E in the T is proportional to omega 6 in agreement with generativity. In the standard ghostful theory, D in the T is proportional to omega 4, so it's a completely net disagreement with the generativity. And also for gravitational wave emission equidistance binaries, generativity predicts that omega dot is related to omega as 11 to 3. In the ghost-free theory, we preserve this relation. In ghostful theory, this relation is lost. Okay, we recover some bunch, but I told you we are still studying this effect. So the message of this result is that at least for order theories of gravity, we have both theoretically and phenomenology some inconsistencies. So let's try to solve this inconsistency, but at the moment we have this inconsistency. Instead, for ghost-free theory, this is a good theory at the moment, and that deserve to be investigated in several framework, like tabletop experiment. Actually, we are doing this in cosmology, primordial gravitational waves. And regarding let me, as I told you at the beginning, let me do this comment. In this beautiful paper, one of the best paper, but I didn't write the authors. Authors are asking Will Berti, which are very high-level scientists. They calculated the gravitational radiation for binary system in Brans-Dicke theory using the green function approach. At some point, they realized that taking into account the eccentricity, even if could be not negligible, they set equal to 0 because calculations are really impossible. With the approach I presented here, we are redoing this calculation in the Brans-Dicke theory, taking into account the eccentricity. Yes, the formulas are very, very complicated, but we are able to get some result like this one I presented here, okay? And the FFT approach is so powerful that we discovered a typo in this beautiful paper. There was a 3/2 number missing here. So that's all. Thank you for your attention.
Thank you. Questions for Gaetano?
Very, very interesting. Two questions. One, you mentioned spin source gravity, and often with torsion theories, one worries that lepton spins in the laboratory and particle accelerators in the sun can also be sources. Is that just too small?
Okay, so if you mean a torsion is small and could have some effect in laboratory, you mean in this sense? Okay, yes. Of course, we have in laboratory, I agree, it's quite impossible to find some effect, except to find some constraint. This is true. But I have to... I have to say that... no, sorry, not here. I didn't tell you all the history, in the sense that I focus on this coupling between G-mu and gravity. Actually, when you turn on torsion, you can have also the coupling with axial current. Now, this kind of coupling could be some effect inside the neutron star or in the early universe.
But not particle accelerators?
Sorry?
In particle accelerators at CERN, would you see any effect?
The CERN you can have so only some bounds, in my opinion. You cannot see this kind of effect. Okay. You need high density, something which is very, very important. Okay. But it's a good point to invest, because you see, there are, so-called portal gravity and portal torsion, in which you have this kind, we have exactly this, okay, you have this kind of coupling, and which means, for instance, that you can see T, the torsion, as mediator of the standard model particles, or mediator of standard model and dark matter particles. And people are working on this kind of ideas.
Okay. And my second question is, do you still have the usual Schwarzschild and Kerr solutions for black holes?
In this framework, I don't think so. No. We have, in fact, one of the projects is to see what up, and in fact, I mentioned at the very beginning, what happens for shadow, ring, photon ring, this, yeah. You have,
Okay, so gravitational wave in spirals could actually affect
This is really first paper in this framework, because we were interested in this particular ghost. Thank you.
Thank you.
Oh.
Any other questions?
Yeah.
So I know you just said this is the first paper on this type of framework, but in your final slide, you said something of like this could give a singularity resolution and a bouncing cosmology. Do you have any intuition what you expect to find for that?
Not yet, but we hope that because we have this new scale, so you cannot go to zero. Your universe cannot go to zero, but when you reach this new scale, there is this bunch. This is what we hope. What we calculation we say is another history, but it is what we expect.
Thank you.
Thank you.
Thank you. One question over there. It's the same time.
Thanks for very interesting talk. I care more about the data analysis part. So could you explain more like how like this model could test with new latest data, cosmologic data?
Cosmology.
Is some
Oh, in this framework, you mean?
yeah, could it
No, we
test
don't
with
have.
you don't test with cosmology?
Because I told you this project arises because I met Shinji one day. Speaking with him, we discussed about this paper. Then from that, we started this kind of work and collaboration. So this all is open at this moment. We don't have, in fact, as I told, we don't have a bound to compare our bound with the existing bound.
Okay.
So everything is there. So yeah, if you have some good idea in cosmology, it's welcome, really welcome. Of course.
Yeah, thank you.
Thank you.